Welcome to Study Loop.
In this problem, we are looking at the rotation of a CD in a CD player. We're given that the laser line is scanning along its grooves at a constant 1.25 meters per second, that the inner radius of the CD is 0.025 meters, and that since the radius is increasing of the circle, the distance, the circumference that it's scanning along increases by 1.55 micrometers per rotation, and that the total time to complete the CD is 74 minutes. So first, we are given these two equations, that r with respect to theta is equal to r naught plus beta theta. So that's just telling us how that is the definition of a spiral. It's telling us how quickly it is increasing in radius as it spins. And then secondly, we are given that ds is equal to rds. And from that, we're supposed to find s with respect to theta. So the first thing to do is to use the formula we have right here. If we take the integral of ds, we'll of course get s, and then we can set that equals to the integral of the other side, r d theta. And since we have what r is with respect to theta, we can just plug that in. The integral of r naught plus beta theta d theta. And then we can just take the integral of that, which will give us r naught theta plus beta over 2 theta squared plus c. But in this case, we don't care about plus c because we know, of course, that it's starting at position 0. So here's our answer to A. That'll be r naught theta plus beta over 2 theta squared. And so we can move on to B, which is asking us to find theta with respect to time. We're told that it's going at this constant velocity, so we know that s is going to be equal to vt. So all we need to do is plug that into this equation. That'll be equal to r naught theta plus beta over 2 theta squared. And then we can move this all over to the same side. Theta squared beta over 2 theta squared plus r naught theta minus vt equals 0. And there we have a quadratic equation. So we can just plug in our quadratic formula, and we will know that theta is equal to minus r naught plus or minus the square root of r naught squared minus 2 beta over 2, so just beta times c is minus vt, and I'll just turn that minus into a plus, all over 2 times beta over 2, or just beta. There's our answer, minus r naught, and we're supposed to choose one of these, plus or minus, and we're going to choose the positive version because otherwise we will get theta is going down because we will be subtracting t. So as t goes up, theta would go down, but we know that we're increasing in theta, so we're going to choose the positive. Square root r naught squared plus beta vt over beta. Okay, next we have to find the angular velocity and the angular acceleration with respect to time. And we know, of course, that omega is equal to d theta dt. So we're just going to take the derivative of this with respect to time. So first we're going to take the derivative of minus r naught over beta. That's just a constant, so that'll be 0. So we can just focus on the rest of this. First, I'm going to take this constant beta out in front, 1 over beta. And now I'll use the chain rule. This is, of course, equal to, the square root is equal to taking the 1/2 exponent of the same thing. So I'm going to write that down, plus beta vt to the 1/2. I will pull the 1/2 out in front, and then subtracting 1 will turn this into minus 1/2. So that will be the same thing as the square root of the same term, but in the denominator. So that will be 1 over square root r0 squared plus beta vt. And now times the derivative of the inside. R0 squared is a constant, so that'll be 0 again. So it'll just be times beta v. Now we can just do some cancellation here. Consolidate. We will get v over 2 square root r0 squared plus beta vt. And then the angular acceleration is, of course, similarly equal to the derivative of the angular velocity. So we just need to take the derivative of this now. So I'm going to pull out that v over 2 in front again. Same thing, this is now equal to this to the minus 1/2, so chain rule, I'll do the outside first, and I will bring down the minus 1 over 2, and now this will become minus 3 over 2, or equal to the same thing, r0 squared plus bvt, but to the 3rd power. And then that will be multiplied again by the inside, which we already know is equal to bv. So consolidating that down, we will get minus beta v squared over 4 times the square root of r0 squared plus beta vt to the 3rd. So those are our 2 answers. I'll just move them over a bit. Let me do that to make room for what we're doing next. And then I will just erase all this to make room. You can just pause the video if you need to look back at it. I shouldn't have erased that part, but it's okay. I can rewrite it. Okay, so next we need to find the final number of rotations that the disk will go through in its 74-minute runtime. 74 minutes, just multiply that by 60, and we will get that is 4,440 seconds. And then we know R0 is the distance between the first groove and the center of the CD. We're given that is 0.025 meters. And then beta is, of course, how much the distance increases per rotation. So that'll be equal to this dr d theta we get, or 1.55 micrometers per rotation. And I'm going to leave that in per rotation because we want to give this answer in number of rotations. So all we need to do is plug in our numbers to our formula. R0 squared minus R0 squared plus square root. I'm sorry, this isn't squared. This one's squared of R0 squared plus beta vt over beta that'll be equal to minus 0.025 plus the square root 0.025 squared plus, I will put the beta at the end because it's going to be long because of the micro in there. The velocity is 1.25 times our time, 4440, times 1.55 times 10 to the negative 6th. Isn't that a long expression? And all of that will be over top of just beta 1.55 times 10 to the minus 6. Okay, and then all we need to do is, plug that into the calculator, and we will get a final answer here of 22,922 down to 3 sig figs will give us 22,900 rotations. And then E is just asking us to graph our equations for the angular velocity and angular acceleration against time. So I've just plugged the equations into a graphing calculator, and this is what they'll look like. Here is the angular velocity with respect to time. As you can see, it doesn't change much over this long run time, but over time the distance is very significant. Okay, and then our acceleration, as you can see, it's negative because it's going the same velocity the whole time, but the radius is increasing. The amount of distance it's going over is getting bigger, so the rotations are slowing down. And as you can see, it really doesn't change very dramatically over a short distance, but as you can see, over the full 4,400 seconds, it's pretty dramatic. So per second, it's not very different, but over the whole course of the CD, it changes quite a bit. And to answer the other question that was asked by the problem, it is not linear, as is plainly evidenced here.